Okay, so this is preaching to the choir a bit, but as we all know, LLM training is a huge computational challenge. This is a figure that I borrowed from the Epic AI blog that shows the cost of training state-of-the-art models. Uh, they estimated the y-axis here is cost in dollars in log scale, and then the x-axis is publication date. And this graph is actually missing a few models, but you can see that training state-of-the-art models now takes in excess of $100 million. And so obviously these models are really large, and you want to train them in reasonable time frames. And so you're compelled to have to figure out how to use thousands or tens of thousands of GPUs to train these models efficiently. So at a high level, people use a couple of different hammers to distribute training. The most popular one that people also use for smaller models was data parallelism, where you stamp out multiple copies of your model, one per available GPU that you have. You have n copies of your model parameters, and then you periodically reconcile gradients across the different GPUs to make sure that uh, every GPU is essentially on the same page. And then another technique that people have been using in order to actually train models that are much larger than the memory capacity of a single GPU is model parallelism, where you split a single copy of the model over multiple GPUs. It turns out that you can do this in a couple of different ways. So you can take each layer or operator of the model and shard it over multiple GPUs. This is called model parallelism in the literature. And you can essentially think of this as doing distributed gems over multiple GPUs. Another way of doing model parallelism is you shard layers or operators in the model across different GPUs. So if your model has four layers, you can assign the first two layers to GPU one and the next two layers to GPU two. And now each of these different techniques have different trade-offs in terms of communication and ability to keep GPUs busy and so on. And I'll talk a little bit about them in the next couple of slides. Okay, so data parallelism, the naive form, you have a full copy of the model on each GPU, and you're doing these reductions of weight gradients at the end of every iteration to coalesce the updates across replicas. Tensor model parallelism, you're taking every layer of the model and partitioning them over multiple GPUs. This is a figure from a paper from some colleagues from about 5 years ago, which shows this paradigm applied to the main transformer block that powers a lot of big LLMs today, right? So the specifics are not super important. But essentially, what's happening here is you have this weight parameter matrix A, and you split it column-wise into these smaller submatrices A1 and A2. A1 is only resident on GPU 1, A2 is only resident on GPU 2. Um, and then essentially each GPU participating in this computation, just two in this example, uh, does its computation on the subset of weights that it has, right? And you can try to partition these weight tensors in different ways in order to minimize communication. What this paper found is you should split the first matrix A column-wise and the second matrix B row-wise, and that's good for this particular model, uh, and minimizes the amount of communication that you need. Um, Obviously, you don't completely eliminate communication. You still need to reconcile some intermediate results that are computed on each of these GPUs. In this particular example, you have this communication operator G that's doing an all reduction of the intermediate outputs computed on GPU 1 and GPU 2, which are Y1 B1 and Y2 B2. Okay. So this is tensor parallelism. Uh, it actually works pretty well on within a server. The way modern machine learning typically works on NVIDIA GPUs today is you have some number of GPUs within a particular server. Usually it's eight that are connected by these high bandwidth interconnects. In the case of NVIDIA GPUs, it's called NVLink, and this is higher bandwidth and lower latency than the interconnects that you get across GPUs on different servers. So the main drawback of tensor model parallelism is that it scales pretty well up to eight GPUs in an NVLink connected 8 GPU server. But then if you wanted to train models if you want to split your model over more GPUs, then you need to pay this communication cost over slower inter-server communication links. Even things like InfiniBand are appreciably slower than NVLink. And so that can really bottleneck scaling if you try to scale this across multiple GPUs. Okay. And so the other idea that people came up with in order to split a single model copy over multiple GPUs is pipeline model parallelism, where you're assigning a subset of layers or operators in a model to different GPUs. So naively, you can think of uh, this timeline diagram where here I'm assuming that the first quarter of layers or operators in the model are assigned to GPU 1, the next quarter to GPU 2, the third quarter to GPU 3, and the fourth quarter to GPU 4. Um, Now, in this scheme, if I just took a single batch of samples, um, I'm bottlenecked by the fact that there are these strong data dependencies across the different GPUs. In particular, GPU 2 can't start processing input batch A here before GPU 1 finishes completing its computation because GPU 2's input is actually the output of GPU 1. Right? And so you go through your GPUs in the forward direction up till you get to GPU 4, right? You have these strong dependencies across GPU 1 and GPU 2 and GPU 2 and GPU 3 and GPU 3 and GPU 4. And then you can compute your loss term on this last GPU because you're done pushing this input through the entire model. And then you can start the backward pass, right? And this is a truncated timeline diagram, but essentially the backward pass would run essentially the same, but just in the reverse direction, right? So you do the backward pass for input batch A on GPU 4 first, and then once it's done, GPU 3 can take the output of the backward pass of GPU 4, do its backward pass, and then you pass that intermediate gradient to GPU 2, and then essentially the whole process is done when GPU 1 is done with its backward pass. Right. But these very strong data dependencies across the different GPUs are heavily limiting to throughput, right? So in this particular simplified diagram, you can see that the utilization of your GPUs is just 1/4 because only one GPU is active at any point in time. And so one thing you can do to relax the strong data dependencies in the computation across these different GPUs is you can instead split this batch A into four smaller independent micro batches, A1, A2, A3, and A4. Now you still have strong data dependencies within a particular micro batch, right? GPU 2 can't process the forward pass of microbatch A1 before GPU 1 is done, and so on. So you still have these strong data dependencies within a microbatch, um, but you each microbatch is now completely independent. And so in steady state, you can see that GPU 4, 3, 2, and 1 can all be active at the same time by processing different microbatches at that instant in time, right? And so now you automatically improve utilization by offering these opportunities for concurrent computation. Right? Now, the problem is not completely eliminated. You still see some idle periods at the start and end of a batch, right? And we call this the pipeline bubble. Uh, but the problem is a lot better than this timeline at the top. Right. So to summarize pipeline model parallelism, you're splitting your layers of operations in the model over many GPUs, and then you're splitting your batch into smaller micro batches and pipelining execution across these micro batches. One nice thing about pipeline parallelism is that you're now only having to do this point-to-point communication between consecutive pipeline stages, and this is a lot less communication than with tensor model parallelism. So, and the trade-off, you're essentially decreasing the amount of communication you need to do, but there's no free lunch. You're trading that off for a pipeline bubble at the start and end of every batch. Okay. And so you can do fancier assignments of layers to GPUs to try to further decrease the size of this pipeline bubble. Details here are not super important, but essentially what's going on here is we are able to decrease the amount of time that GPU 4, for example, needs to wait until it can start processing micro batches. But we're trading that off for more communication. Okay. Now, what we realize is that each of these individual schemes are nice, but they have trade-offs. And if you want to train really large models at thousands of GPU scale, uh, you're eventually going to hit some scaling limits for each of these parallelism schemes individually. So for example, with pipeline parallelism, you can only really scale this up to the number of model layers that you have. Um, like the largest models that we train these days have on the order of 100 transformer layers. So if you were to only use pipeline parallelism, you could only train a model with 100 GPUs if it had 100 transformer layers, right? Um, and so essentially you get to a particular scale where you need to combine a lot of these different parallelism schemes in order to efficiently train models at that larger scale. It also turns out that naively combining different forms of parallelism can lead to poor throughput. So, for example, if you just increase the tensor model parallel size past the NVLink domain size, past 8 GPUs, your tensor model parallel communication is going to very quickly dominate. And that's going to limit the throughput you see in your distributed training setup. And so, if you're going to combine these different forms of parallelism, you're going to have to reason through the interactions between the different parallelism schemes. So let's quickly go through an example of what this looks like for just tensor and pipeline model parallelism. So here I'm going to assume that the total number of GPUs that I have is n. Uh, the tensor model parallel size is T, and the pipeline model parallel size is P. So a constraint with just having n total GPUs and only using these two forms of parallelism is that T times P is going to equal n. Now I can quantify the total fraction of time I spend in the pipeline bubble. So I can quickly scroll back to the slide here. Um, the pipeline bubble size is actually equal to P minus one micro batches of work, right? So in this particular case, my pipeline parallel size is four, right? And GPU 4 essentially needs to wait for three micro batches worth of forward work at the start of a batch, and then three micro batches of backward work at the end of a batch. right? So the size of my pipeline bubble in general is going to be P minus one, where P is the pipeline parallel size. Um, So the denominator here is P minus 1 times TF plus TB. TF is the amount of time you spend in a micro batch in the forward pass. T sub B is the amount of time you spend in the backward pass of a micro batch. And I'm going to compute the ratio of this pipeline bubble size to the ideal amount of time I would need to spend to process M micro batches, right? So I'm assuming that a batch is composed of M micro batches, and I'm going to compute the ratio of ideal time I spend doing this computation uh, uh, to the time I essentially spend doing no work. Right? So this is essentially a measure of uh, how long you're wasting compute, basically, right? Like how long are your GPUs idle in this parallelism scheme? So now you can quickly see that this T sub F plus T sub B factor cancel out in the numerator and denominator. And so the pipeline bubble size is just going to be P minus 1 divided by M. And then I can do some further arithmetic. I can observe that P is just going to be the total number of GPUs you have divided by tensor parallel size. It's going to be N divided by T minus 1 divided by M, right? And so if M is an input and N is, well, if M is constant and N is also constant, then I now have a function of, uh, I've been able to express the pipeline bubble size as a function of the tensor model parallel size, right? And so I can quickly observe that as the tensor model parallel size increases, the pipeline bubble size decreases, which is good, right? You're spending less time in these, uh, uh, you're spending less time idle doing no work. However, increasing T has this other counteracting effect that if you increase T beyond the number of GPUs that you have in a server and you have to go beyond NVLink, then the communication that you need to do as part of tensor parallelism is now cross-server and slower. Right? So you can see that there are these two factors that are kind of at odds with each other. And so we can actually see how these factors play out with real experiments on silicon. So here I'm going to show throughput for a 162 billion parameter GPT model on 64 A100 GPUs. So on the y-axis, I'm going to show throughput per GPU. So for all of these different configurations, I'm going to use 64 GPUs. Um, and higher number is better, right? So a higher throughput per GPU means in aggregate, you're also doing, your aggregate throughput is also higher. And on the x-axis, I'm going to sweep a different model parallel configurations that use 64 GPUs. So, for example, the leftmost point here, the pipeline parallel size is going to be 2, and the tensor parallel size is 32. And then I'm going to gradually increase the pipeline parallel size and decrease the tensor parallel size. And these are the results for two different total batch sizes, which translate to two different numbers of micro batches in the pipeline. And you can see this very distinct effect where the throughput initially increases as you increase uh, the pipeline parallel size, but then it starts decreasing. And the reason why you have this inverted V kind of effect is precisely because of these two factors that I talked about on the previous slide, right? As you on the left side of this figure, you need to do tensor parallel communication across servers, which is slow. And then on the right side of this figure, your tensor parallel size is really large, which means that your pipeline bubble is also really large, right? And so you essentially get low throughput on the extreme ends of this figure for completely different reasons. But you essentially see a sweet spot in the middle of this graph where the tensor parallel size is 8 and the pipeline parallel size is 8. And the reason why eight is a magical number is because eight is essentially the NVLink domain size, right? It's the number of GPUs that are connected by NVLink on a server. So essentially increasing the tensor parallel size beyond eight means that your tensor parallel communication is across slower links, and that slows things down. It turns out in general, this configuration space is pretty challenging to navigate. So we talked a little bit about the degrees of these different parallelism dimensions and how that can affect end-to-end throughput. Turns out that the pipeline schedule that you choose also has trade-offs. Um, So here I'm going to show, again, same setup as before, slightly different model on 96 A100 GPUs. And I'm showing the two schedules from a couple of slides ago, right? The non-interleaved and the interleaved schedule. And you can see that depending on how many microbatches you have in your pipeline, the gap between the non-interleaved and the interleaved schedule can change. Basically, the interleaved schedule is much faster than the non-interleaved schedule at low batch sizes, but the gap decreases because the interleaved schedule has more communication as you go to larger micro batch counts. Right. Okay, so the configuration space is also affected by global batch size. Also, this other hyperparameter called the microbatch size that I didn't get into for time reasons. But each of these can influence the amount of communication you need to perform, the size of the pipeline bubble, memory footprint, convergence rate, and so on. And we talk about how to reason about a couple of these different things in the paper that was assigned to you. So I have a couple of more slides about more forward-looking stuff. Abhinav, how much time do I have left? You're muted.
Yes, sorry. Yeah, if you have a few more slides, that's fine. We can still go over
Okay.
them.
Okay. Sounds good. One observation from over the last couple of years has been that SOTA models no longer are just having more parameters. This is a really nice paper from DeepMind a couple of years ago that essentially argued that instead of training a really large model for over a small amount of data, we should instead train a relatively smaller model over much more data. And so these are called, this regime is called computing a compute optimal model. And it has some profound implications on how we should think about building systems for efficient model training. In short, one thing that we need to be cognizant of is that we're increasingly going to have to use more GPUs to get results faster, instead of using more GPUs to just train, to just fit more model parameters in GPU memory. And so another way of thinking about this is we need to be able to efficiently train models in regimes where the batch size per GPU is much smaller. So you might think, okay, what's the big deal? Like, what actually happens when the batch size per GPU is small? So there are a couple of reasons why this makes scaling more challenging. The first is related to something we've talked about extensively today, which is that if the number of microbatches in a pipeline is small, your pipeline bubble, which is P minus one divided by M, is going to be large, right? Because if the number of microbatches, which is M, decreases, then this denominator essentially gets really small and the whole term blows up, right? So one immediate effect of being in this low batch size per GPU regime is your pipeline bubble can become really large. The other effect of being in this regime is you need to do data parallel communication more frequently. So let's say we initially had a global batch size of four and just two GPUs. Uh, essentially what happens here is every GPU does two samples worth of computation, and then does the gradient reduce operations that are needed, and then you do the next batch of two samples each in parallel, and then you do the necessary communication and so on, right? So effectively, if you look at this in terms of wall clock time, you do a data parallel communication every two samples in this regime where you just have two GPUs and a global batch size of four. Now, if you scaled up to four GPUs, every GPU now only has one sample. And so in terms of wall clock time, you're effectively communicating more frequently, right? And so if you thought about your compute communication ratio, that's decreasing as you increase the number of GPUs. And so it becomes really important to not only decrease the amount of communication that you have, but also try to hide it with computation as much as possible so that you don't feel the full brunt of exposed communication. So very concretely, for data parallel communication, let's say you have some model with some layers. Here I've denoted the layers in different colors. The naive way of doing this is you finish your full compute in terms of both. So here I'm only showing the backward pass computation. But you finish all of your backward pass computation, and then you launch this single communication kernel that does the gradient reduction for all the parameters that you have um, in your model. It turns out that you don't actually need to wait till the end to do this communication. There are some data dependencies here, but they're only data dependencies within the same color, right? So this light yellow layer one, it turns out that I can actually do the data parallel communication for it as soon as I'm just done with the backward pass for layer one. Right. So now you can do this much more fine-grained overlap between compute and communication. And the upshot of this is you don't pay the full communication cost at the end of all of your computation. Instead, the only exposed communication is the communication corresponding to the last layer in the model, right? And so this is an idea that allows you to even if you need to communicate a lot and communicate frequently, you don't need to pay the full brunt of communication, right? You can hide the communication behind most of the communication behind compute, and so the exposed communication can be greatly reduced. So we can take all of these different tricks um, and put them all together when training really large models. So our group trained a 340 billion parameter model um, early last year on 6,000 GPUs. We used a tensor parallelism size of 8, pipeline parallelism size of 12, and data parallelism size of 64 or 96, depending on whether we use 6,000 GPUs or 9,000 GPUs. And we got a net throughput of 405 teraflops per GPU on 6,000 GPUs. The peak uh, compute throughput of the H100 GPUs that we use is 989 teraflops. So given this aggregate number includes memory bandwidth bound operations and compute operations and idle periods and data loading and so on, this 41% number is pretty good at scale. We can also run like a weak scaling experiment where we increase the size of the model with the number of GPUs. On the left side of this figure, I have a 1.7 billion parameter model on, I think, 48 GPUs. And I can gradually increase the size of the model and the number of GPUs I'm using. And I can get to 6,000 GPUs and 462 billion parameters. And using the techniques that I've talked about today, we can get to a aggregate throughput of 2,800 petaflops. Just by being careful about how we split the computation over multiple GPUs and also carefully hiding communication behind compute. Okay, so I'll just wrap up here. Yeah, so all of our all of the techniques I talked about is available in our open source repository on GitHub. And I guess the two key ideas I want to communicate are if you're really training at scale, you should carefully think about how you're composing these different forms of parallelism. And overlapping compute and communication is really important if you actually care about this low batch size per GPU regime. And with that, I'm happy to take questions.
Okay, let's thank Deepak.